Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. My name is Mitchel Affandi, and today I will walk through antenna measurement based on Module 6. There are four parts. First, the basic requirements for a valid measurement. Second, how we measure the radiation pattern in azimuth and elevation. Third, how we measure polarization. And fourth, how we measure gain with two methods. Let's start with why measurement even matters. We can design antennas through analysis and synthesis, but in real life, many antennas have complex shapes and feeds, so they can't be solved fully on paper. And that's where measurement comes in. It lets us verify the theory. And one thing to remember is that most antennas are measured as receivers. So these are the four parameters we'll cover: requirements, radiation pattern, polarization, and gain. First, the measurement requirements. The ideal condition is a uniform plane hitting the antenna under test. Uniform means the phase and the amplitude stay constant across the whole aperture. Let's focus on phase. From the geometry, the phase difference across the antenna is about d squared over 8r. To make that error zero, we'd need infinite distance, which isn't realistic. So instead, we set a tolerance. Kotler, King, and Co. use 22.5 degrees, which is the same as lambda over 16. Plug that in and we get the far field distance. R minimum equals to d squared over lambda. This is the standard rule for how far apart the antennas should be. The second requirement is about amplitude and the environment. For amplitude, we want it uniform across the antenna. That means a small taper, low ripple, and clean cross polarization. As a guide, keep the field variation within 0.25 decibel. The environment matters just as much. We want a stable frequency. The far field condition meant no reflection and low noise. The impedance and polarization should also be matched, and the antenna aligned to its main beam. Ground reflection is a big one. We reduce it with tail fiberglass towers, RF absorbers, and a source that radiates weakly towards the ground. Indoors, we can use an echoic chamber, which also works as a Faraday cage. Now, the radiation pattern. We measure it on a sphere of constant radius r around the antenna. A full 3D pattern would take forever to capture, so instead, we take two flat cuts that are perpendicular to each other. Here's the measurement chain. A source antenna, log periodic or dipole below 1 GHz, or horn or parabola over 400 MHz, a positioner that rotates the antenna in azimuth and elevation, a stable transmitter, a receiver from a simple detector up to a heterodyne with PLL, and finally a recorder with a data processor. Now let's look at those two cuts. The azimuth cut keeps theta fixed and sweeps phi. In practice, you rotate the antenna around the vertical axis. That gives you the horizontal plane. The elevation cut is the opposite. You keep phi fixed and sweep theta, rotating around the horizontal axis. That gives the vertical plane pattern. Together, these two planes give us the E-plane and the H-plane patterns. From them, we read the main lobe, the side lobes, and the back lobe, the half power beam width at -3 dB, and the front to back ratio. Next, polarization. And polarization is the path traced by the electric field as it moves, seen in the plane facing the wave. It's usually elliptical, built from the theta and phi components, and it changes depending on the viewing angle. We describe it with four things: the axial ratio, the sense of rotation, whether it's right or left-handed, and the tilt angle tau. There are three families of methods: partial, comparison, and absolute. The most common one is the polarization pattern method. You take a simple linear probe, rotate it, and record the signal level at each angle. That gives you the axial ratio and the tilt. The only thing it can't tell you is the sense of rotation. Now, gain. The first method uses two identical antennas. It's also called the reciprocity method. One antenna transmits, the other receives. We compare the power using the Friis equation with distance r known. Because the two antennas are identical, their gains are the same. So the gain in dBi is 1/2 of 20 log of 4 pi r over lambda plus 10 log of the receive over transmitted power. The second gain method is for when the antennas are not identical. We use three antennas. We measure them in three pairs: 1 and 2, 1 and 3, then 2 and 3. Each measurement gives us the sum of two gains. Call those sum ABC, for example. Then we just solve the three equation. G1 is A plus B minus C over 2. G2 is A minus B plus C over 2. G3 is minus A plus B plus C over 2. And that gives us all three gains without needing any reference antenna. So, to wrap up, the requirements: a uniform plane wave with r at least 2d squared over lambda and field within 0.25 dB. The pattern: two perpendicular cuts, azimuth and elevation. Polarization described by axial ratio, sense and tilt. And gain: the two antennas method when they're identical, or the three antenna method when they are not. That's the summary. Thank you for watching. This is Mitchel speaking. Wassalamualaikum warahmatullahi wabarakatuh.